Note that I could have drawn an infinite number of rays here, and they should all cross here. It just gets too crowded if I draw that. Yeah. Okay, this is the one that I really struggle with. You thought I struggled with the other one. But wait, there's worse. Okay, so this one comes in paraxially. What's it do? Passes through the focal point. Well, that's probably miserable, but you guys have come to accept mediocrity. If I try and draw the one that passes through the focal point on its way to the mirror, this time we have a problem. Why? It's already in front of the focal point. And so instead, I'm going to draw the one that is on the line that connects the focal point to the point of interest. What does this one do? What's the one that goes through the focal point on its way to the mirror do? Comes out paraxially. Oh, good golly. That is not paraxial, but it's the thought that counts. You guys have lines on your paper. That's the excuse I'm using. Oh no. Cleanse by fire. Does that seem reasonable-ish?
Yeah.
Cheat, because I know where this is supposed to wind up. Yay? And so what kind of image do we get this time? So virtual, upright, magnified. This one was the original? Real, inverted, and magnified. Yay?
Yeah. We're talking about lenses, correct?
No, we're talking about mirrors.
Still mirrors?
Yep. That's why it's reflecting and not refracting. Yay? So for our convex mirror, so these are concave cases.
What is the difference between the mirror, that one, and the very first one we did?
What's the difference between these two?
and this one right here. The very first one you did.
You mean this?
That one.
No difference.
No difference, they're the same.
Yeah, absolutely no difference. So what I asked was if people wanted to see ray tracing diagrams. And the answer was yes, so.
Okay, we just repeating. Okay, perfect.
Okay. So. If it comes in paraxially, what does it want to do?
Reflect through the focal point.
Through the focal.
It wants to reflect through the focal point. The focal point, though, is back here, and so what's it going to do? Yeah, exactly. I don't know why I'm trying to be so careful with this, because I didn't actually draw a spherical mirror, or even a segment of a spherical mirror, so there's no way that even if I drew this.
We get what you're trying to do.
And I hope you'll appreciate it too. I'm here to entertain with my poor artistry. It's a service I provide to make people feel better about their own drawing. This one wants to get to that focal point on its way to the mirror. What does this one do?
Reflect.
Comes out
Paraxial.
paraxially. Okay. Again, the observer assumes that that ray has been traveling paraxially since inception. And then we draw one more. We draw many more if we wanted to, but does that seem fair enough? Yay-ish. And so our image, what can we say about this image?
Upward.
Upright, virtual, and magnified. Not the same size as the original, yeah?
So magnify can be smaller or bigger.
Yep. Kind of in the same way that when we speak of acceleration, maybe outside this classroom, you think of acceleration meaning it's going faster and faster over time. But in your Physics 130 class, we also said it was accelerated if it was going slower and slower over time, or even just kind of. Yay? Okay, so let's try an example before I start trying to get to refraction. So So, I'd like to describe the image, position, size, upright or inverted for that case. How do we do this? What equation do we use?
The one that we found earlier. The 1 over
F, 1 over F equals 1 over P plus 1 over Q? No.
True story.
True.
What is F? Positive or negative?
10.
positive.
Positive. How do you know?
The absolute.
Oh no. So I did that so that I didn't have to tell you whether it was positive or negative.
Wait, positive because it's concave.
Concave.
Because
Okay.
concave tells us F is positive.
Oh, okay.
Hooray? Yeah, so on exams,
That's what you're gonna get.
that's how I'm gonna try and
Wait,
make your
let's-
life harder.
You're gonna provide the same conventions?
No.
No?
No.
That's not fair.
One of my absolute terrors, and I probably shouldn't put this out into the world, right? Don't express your terror to the world, but is that we now have all these whiteboards on the walls. And my absolute terror is that students are going to be studying right before the exam and leave notes on the walls.
Oh my God.
But I do want you guys to study. I just don't want you guys to leave notes on the walls and then go out to the restroom.
Is that why you took it down?
No, it had bubbles, so we made the contractor take it down so that they could put it back up without the bubbles. So,
It was a good structure.
what else?
1 over P is 25. 1 over 25.
P is what, Q is what, I already forgot. P is object, right?
So in terms of fives, I guess I could even do this in terms of multiply top and bottom of this by 2.5.
I think it's
Since I can do
16.
that, right?
100,
Q is
10,
16.6.
104, 106. Oh yeah, I can do it also. 6 over 100. So 3 over 6 over 0.06. Oh no, we have to flip it also. Damn, so it's wrong. 100 divided by 6. Damn.
Yay?
Yeah. Yes.
Is it upright or inverted? What equation can we use for this? Somewhere on here.
Tan data. Oh, the magnifier.
What's this again? It's concave, right?
It's converted.
Concave. Concave.
So minus over what?
5.
Some kind soul with calculator, bail me out.
Negative 0.67. No, negative 0.68.
6, 8?
Yeah, it's 8.
I mean, I don't care. Yay? Is the image upright or inverted?
Inverted.
How do I know?
It's negative.
So the magnification will be negative when we have an inverted image. Yeah. This also passes the smell test, right? In that, where is the object compared to the focal length? Is it nearer to the mirror body or further from the mirror body? Is the object it's farther, so is that more like this case or more like this case?
The first one.
It's this one, right? Where the object is further away from the mirror than the focal point.
Yeah.
And so what kind of image do you get? You get a real inverted image, yeah? Yay? What about B? Help me write out the equation. 1 over 10 equals 1 over 10 plus 1 over Q. Uh-oh. So what does that say about Q?
Oh, no. 0. 0 would be infinite.
Oh, Q is infinity.
Q is formed at infinity. Yay?
Yeah.
Can you think of a case where you've seen something like this?
In space?
Oh, well, like,
Kaleidoscope.
Code is infinite.
Mag light? Flashlight?
Huh?
Laser.
Flash.
You know that they have that ability to twist it to adjust the bulb position?
Uh-huh.
What are you actually doing?
Raising it up and down.
You are trying to get the filament of the bulb to be on the focal point axis. What will that do? Well, it's going to try and cast an image of that filament off at infinity, right? It's going to send that beam out far. Yay?
It is like the file in the car, front.
You know, I don't really think that my headlights are as collimated as what you're getting with a mag light. I do feel like they've purposefully let the beam spread, probably to give me more sight of the concrete in front of me. So this is, and that there's probably justification for that. But a mag light, I mean, this is kind of the aim, right? Or I'm not promoting any particular brand of flashlight. Whatever flashlight you are most fond of, substitute that one. What about when the object is 5 centimeters? So first, before we even proceed, is that more like this case or more like this case? A or B?
B.
More like B, yeah?
Yeah.
Why? The focal length is
longer.
is 10 centimeters, the object position is 5 centimeters, yeah? So what kind of image are we expecting?
Magnified, right?
Upward.
Magnified and upright and virtual, yeah? Let's see what happens. So 1 over 10 centimeters is equal to 1 over 5 centimeters. I've dropped sig figs because I'm not actually turning this in. I multiply top and bottom by 2, and I get the I. So 1 over 10 minus 2 over 10 is minus 1 over 10. So Q should be minus 10 centimeters. Is that right?
Yeah.
Did I get that right? Okay, thank you. So what's the magnification? So minus 10 is 10 centimeters over
10.
what's P here?
Of
5. So I have a magnification of 2. As expected, this thing is big, right? Yay? So the fact that it's a positive magnification tells me what? That it is an upright image. Yay? And they all have tapped over after? Do you want to try this for a convex mirror, or are you guys thinking that you can sort out 1 over f equals 1 over p plus 1 over q? You want to try an example?
Please.
So
Let's
we're
try one with
doing
a convex.
things like this, right? What are we doing?
First we have to find Q, so use the equation 1 over f.
Yay? So help me plug in values.
Negative.
Remember, I'm not a nice person. Ask my brothers. But when you ask them, kick them in the shins. As long as they're there with you. Coming back to, I don't know where this was, our sketch, what kind of image are we expecting? Virtual, magnified, and upright. Let's see what we get. So let's see, if I multiply top and bottom of this one by 8, is that right?
No.
By 4
No,
is
that's
easier.
not right.
By 4 you make
By
a 10
12.
or
By
something.
12, thank you.
By 4 is 1.
Let's see, minus 12 minus 1 is minus 13, so 3 over 13 negative.
4.2.
That feels like just under a quarter. Lovely weather we've been having lately.
Very lovely.
think that it's supposed to rain though. We could use the rain.
Later tonight.
Now we find.
Maybe again on Saturday. Anyone with a calculator not want to hear the weather report?
It's coming in at 11. Can I sleep overnight?
How do we get to M again?
H.
Minus Q over P?
Negative 0.23 over
And 177.
3.
0.277.
What did you get? I apologize.
0.07. 0.077.
Yay?
Yeah.
So what does this tell us? The fact that the magnification is positive? It is in fact upright. The fact that Q is negative, what does that tell us? Virtual image. So upright, virtual, and M isn't 1, so it's magnified. Yay? They all love happily ever after, at least for now? Okay.
But when would the object position ever be a virtual object?
That's what I was saying. We could get to this if, let's say I used a lens in front of a mirror and so I'm going to use the image from the lens as the object for the mirror, but the image for the lens would be back here.
Oh, I see. Okay.
That works. Hooray or not hooray?
If the magnet, if M equals 1, does that mean the image is not?
Unmagnified.
Unmagnified.
And note that when we had our plane flat mirror, we had that P is equal to Q. And so you'd have minus P over P is plus P over P is 1. So plane mirrors are unmagnified.
If it's -1, it's still magnified.
If it's -1, I would still say that it's unmagnified. But
Will be just virtual? Is that what the negative one?
it'll wind up being virtual.
Oh.
Oh wait, no. I would think that's real because that means it's
Because by definition, M is negative Q over P, right?
because
It would be virtual.
our inverted are usually upside down, right?
Yeah.
That's not on this list.
Like he take a picture. Use your camera.
That would probably take multiple instruments, like more than one mirror, or more than one lens, or a combo.
If it's negative.
If it's negative and 1,
Oh.
try and think how I could get to that with just one device. Let me think about that more. I don't see an easy avenue there, though. I think that you probably need at least 2. Yeah, let me think about that. There might actually be a way of getting there.
So if for a spherical segment mirror, if there's a ray of light that's hitting the mirror paraxially I guess, it always hits on the axis half a radius away from the center?
In our ideal world, yes. So in practice, I think you can probably already tell the answer is no. If you stick to this region of the mirror, then yes, anything paraxially in that. But as you make, wow. As you make the mirror subtend a greater and greater angle, it really doesn't all come through the focal point. The focal point kind of shifts. So typically when you're talking about a spherical segment mirror, you're not talking about like half of a soccer ball. You're talking about,
Oh yeah, yeah.
as long as you do that, then yes, a paraxial ray goes through the focus.
Also, when you say concave mirror, are you just always talking about?
The inside of the soccer ball. So imagine that you put silver paint all over the inside of a soccer ball.
But is it always a segment of a sphere?
If I say concave, I'm going to mean that. We're not going to deal with other geometries other than spherical. So a lot of your fancier telescopes aren't using spherical optics. But for us, we're not going to deal with that because the geometry is just harder. The thing that still has to be true regardless of the curvature of the mirror is the instant angle is reflected angle. Five-ish minutes? Okay. I'll start this. We won't get all the way through this. So we have imagine that you have a glass rod and you take some really, really fine grit sandpaper and you curve over the top so that the top of it is part of a sphere. Does that make sense? That's all I've done here. So trying to show you that the curvature here is spherical. It's just on top of a cylinder. Oh, good golly. It's the thought that counts. And one out here and two in here. Start by putting an object, or at least a point on the object there, and okay, I thought I picked up the lens by fire pen. You laugh, but we lose more pens that way. So How does Snell's law work?
Two different.
So we have n1 sine theta 1 is equal to n2 sine theta 2.
Yeah.
But what are theta 1 and theta 2? How are we defining that?
Theta 1 is I.
So there's the center, right? So what is theta 1? Like how do we,
Is that the angle when the ray is going?
so when we have just this simple flat surface, right? Okay. So what is the angle measured with respect to?
Normal.
Respect to the normal. So how am I going to get a normal here for my
You can draw one parallel to the.
does that work? And so where would theta 1 be?
Outside of inside
Oh my
and
god,
the red.
it should be.
Coming back to this picture, what's theta 1?
It's above the top red line and there between the normal.
Yay?
Yep.
Does that work?
Yeah.
And so what's going to happen here?
It's gonna.
Gonna bend.
I did
towards-
this with n1
towards the
less than
normal.
n2. So, uh-oh. Something like that? Does that work for you guys? So then, I am out of time.
Oh.
I will pick up here on Wednesday. As always, you guys are awesome. Have wonderful days. Thanks for stopping by. Don't be strangers. Enjoy your days, but not so much. I'll see you next time. I am, let's see, 3/5 done grading your test. So my
Oh my
sincere hope is to have it returned to you by Thursday.
Professor.